Hi there, this lecture is about integer overflows. So, what can we say about integers that is relevant for security? Well, integers have a fixed size. This is convenient, of course, but it also means that each integer has a limited range. So, question is, what happens when we go outside this range? It turns out in many cases this is actually responsible for security vulnerabilities. So, some typical ranges are shown here. Of course, we should keep in mind that the range is defined by the number of bits. So the number of possible values is pretty much 2 to the power of the number of bits. And then there's the difference between signed and unsigned, where signed numbers cannot express numbers that are equally high as the unsigned ones, but the signed ones do allow for negative numbers, splitting the range more or less in half between positive and negative numbers. As I mentioned, integers have a limited range, so at some point there are numbers that do not fit in. What happens if we still try to put one of those numbers into the integer? Well, the CPU will still compute the result. However, it discards the bits that do not fit. So the result that you get has some of the bits correct, but the others that do not fit have simply been removed. Now, what is the impact on the result? So let's look at an example in decimal to see what happens. So let's say that these are actually decimal numbers that are fit into integers of 3 decimal digits. Now we add 567 and 456. The result is 1023. This doesn't fit because we had only 3 digits. What do we do? Well, what the CPU would do, it discards the one at the start, because this is the digit that doesn't fit. So rather than 1023, the answer actually becomes just 23. Effectively, although this is the wrong answer, of course, it could be argued to be the right answer to a different question. And that question is not the regular computation, but a computation modulo 1000. So if we only care about the remainder after dividing by 1000, then this answer is still correct. In the more general case, we basically compute the numbers modulo 10 to the power n, where n is the number of digits. So what happens in the binary case? Well, exactly the same. Results are effectively computed modulo 2 to the power n. Now this means that the result is always nicely well defined, and many results based on the math of modulo arithmetic still hold in a sensible way, even if the answer is incorrect. However, this is not necessarily what a programmer expects. If a programmer doesn't realize that their numbers might go out of range, then the result modulo 2 to the power n could be very unexpected, and this could cause all sorts of issues that also have a security impact. So, unexpected results for the programmer. When do we get these unexpected results? Well, generally speaking, this can happen in case of casts involving integers, computations involving integers, as well as comparisons. So let's take a look at some examples of what could go wrong. Let's classify integer overflows. So the first type is truncation. So if we cast an integer to a smaller type, and keep in mind, this could happen implicitly. So if we assign an int to a short, then there will be an implicit truncation, even though it's not obvious from the code. So in that case, what happens? The extra bits are discarded. So part of the integer is lost when we store it into a short. And if the number is too large to fit into a short, it will be truncated. Now another case is arithmetic overflow. So let's say we add 2 numbers and the result is too big to fit. This is equivalent with the decimal example I showed. So it discards the carryover that would have otherwise gone in the extra bits that were needed. As a result, typically the answer wraps around the 0 in case of an unsigned number, or the minimum versus maximum number in the case of signed arithmetic. Now finally, signedness is in itself also an issue. So it's possible that Incorrectly, a negative integer gets interpreted as an unsigned integer. The C language has some complex rules about this that may be confusing, especially to new programmers. And so it can happen, if you're not careful, that your integer is cast implicitly to an unsigned type. Well, if you then compare it, you're incorrectly interpreting the sign bit. And a very small number, because it's very negative, suddenly becomes a very large positive number, which would be very unexpected for most programmers. The program you see here is a very simple example of an integer overflow through truncation that has a security impact. So in this case, what happens is the attacker passes in a string and we make a copy of the string. We allocate memory to fit exactly this string. However, with our carelessness, we actually use a short, whereas the length of a string would be of type size t, which on 64-bit systems is typically 64 bits. Now a short is only 16 bits. So obviously, if we have a very long string, the length will not fit in an unsigned short. So what happens in this case, we use the length that has been truncated implicitly. So just because of the assignment, there's an implicit cast to a smaller type. And this value that has been truncated is used to allocate the memory. So in the malloc call, we add 1 for the null terminator and then allocate this amount of memory. Now, if the amount of memory, if the length has wrapped around, it means that we're allocating too little space. And then next, the string copy will go out of bounds in the buffer, which is obviously a security vulnerability. So to make matters more concrete, let's say that the attacker sends a string of length 65,537 bytes. Now this happens to be 2 to the power 16 plus 1. What a coincidence. What happens here? Well, as I said, you essentially get modular arithmetic. And the modulus in this case is 2 to the power 16, which is 65,536. So when we assign the length to the unsigned short, what happens is it is truncated by computing the remainder after dividing by 65,536. And the result is simply 1. Here we can see that the number was not picked as a coincidence, right? This is exactly 1 larger than the number of possible numbers in an unsigned short, which is 16 bits. So we see then on the next line that len is just 1. We add 1, so we're only allocating 2 bytes. And then we're sending the full string into this allocated buffer, which obviously causes a massive heap overflow that we could exploit. The next example is an arithmetic overflow example. In this case, we perform a check. We verify that the string length actually fits in an unsigned short. If it does not, we just return 0. So we're basically telling the attacker, this cannot work. However, then we continue. We still perform the assignment, and moreover, we add 7 because we want to add to the string. So if we add 7 to this short, then we get a problem. Because even though the number itself was verified to fit, the arithmetic will overflow. The number after addition does not fit. And after all, we still end up truncating. So in this case, the attacker will give this number, which is 2 to the power 16 minus 1. So 65,535. Now, after adding 7, which was the number of bytes that we're going to add in the string, after adding 7, what happens is that we're only left with 6 if we remove the 2 to the power 16 modulus. So we're allocating just 6 bytes and overflowing massively in the buffer. This example shows the final class of integer overflows, namely those based on signedness. Now in this case, we parse a number that's input by the user. and put it in a short. Now, if you're familiar with C, you should know that the short by default is signed. So this is a signed integer of 16 bits. Well, next we perform a check. We make sure that the length is actually large enough. Is actually not too large, because we only have 16 bytes available in the string. Now, for whatever reason, we put this number into an unsigned short. So this unsigned short cannot store negative numbers. And instead, we're going to be interpreting the sign bit now, not as negative, but as positive. If, for example, we put in -1, we actually get the largest number possible, which is 65,535 again. Right, so this is what we end up with for the length that we're going to write. So we did the check, the comparison, with a signed value. And now we perform the copy with an unsigned value. So the memcopy will actually copy much more than the check assumed. So this of course means that again, we have a potential for buffer overflow due to an integer overflow. Now, this example of course looks very contrived with the assignment in between to an unsigned value. In reality, it will be much more subtle. So in many cases, we have parameters that are signed or unsigned. And assigning a value to the parameter will also cause this issue, even though we don't see the type. A common one, for example, is size_t, which is used to store sizes of memory objects. On 64-bit, this is a 64-bit number, but size t is unsigned. If we put a negative number there, there's going to be an implicit cast that makes it unsigned. So now, if we have a negative number, we're actually going to try and copy lots and lots of stuff, which is obviously bad. Here we have another example. Now, please pause the recording and take a moment to take a look at this code. See if you can find the vulnerability. So what is this code? Well, this code is presumably in a network server. So we pass in a socket file descriptor and we're going to read some data from it. Now, of course, network protocols must be strictly defined. And as we know, the int and long actually have sizes in C that depend, in theory at least, on your system. In practice, in many cases, of course, they are the same. So for 64-bit systems, we more or less expect int to be 4 bytes and long to be 8 bytes, at least on Linux. But if we're interacting over the network, we must assume there can be all sorts of systems. So let's make sure that rather than using the default C types, we use a type that does not change in size. Now this is, in this case, uint16t. Here, unlike the previous example also, we have a good reason to limit the size. If we want to reduce the amount of network traffic, improving performance, it makes a lot of sense to use only 16 bits, if we can. So, we have this 16-bit integer, and we read it from the connection here. We're reading it from the socket from the other end. So this is fine. There's no overflow here. We just read the number. However, next we're going to add something to it. So we have the string buffer, and we add the length of the buffer to the length of the string that we received, computing a total. Now this is an issue. We know that the length fits because we read it from the user, who might be an attacker of course, but we read it in 2 bytes and we know that there can be no values outside this range specified. However, now that we're adding, we can have an arithmetic overflow and we can go outside of the range. So in this case, this goes wrong because now the total is incorrect and we have a check which makes sure that the total fits into the buffer. Well, if there was an integer overflow here, the total will now be a very low number, which will obviously be less than the size of the buffer. So this check becomes useless. Well, this obviously means we now have a buffer overflow caused by an integer overflow. Then finally, how would you exploit this? Well, the addition that is stored overflows for large length, and the length is attacker controlled. So what happens here is if we specify a length of 2 to the power of 16 minus 1, so 65,535. If we add this to the length of the buffer, which is 23, then we get a number which is too large to fit in 16 bits, and it's truncated to just 22. Well, 22 is obviously less than the size of the buffer, size check is bypassed, and we end up reading all those bytes from the network connection. So this is only limited by how many the attacker sends in the end. It is important to note for an attack like this that if you go a lot over, there is a risk that you're actually going to fault. So if you don't have enough memory allocated to satisfy the entire request, this might actually end up protecting the application. So for example, the read system call might return e fault in this case and not actually perform the read because there's not enough memory available.